Hey, we are back with a new section of this video course, Functional and Reactive Programming Features. In the previous section, we dived into more advanced class design. In this section, we will start by writing generator functions with the yield statement and using stacked generator expressions. Then, we'll apply transformations to a collection, see how to pick a subset, that is, the 3 ways to filter, summarize a collection, and combine map and reduce transformations. We will also learn to implement the there exists processing, creating a partial function and simplifying complex algorithms with immutable data structures. At the end, we will explore about writing recursive generator functions with the yield from statement. Let's move on to the first video of this section that deals with writing generator functions with the yield statement. In this video, we will define a function to process source collection, use the yield statement, and collect the data into a proper list. The idea of functional programming is to focus on writing small, expressive functions that perform the required data transformations. Combining functions can often create code that is more succinct and expressive than long strings of procedural statements or methods of complex stateful objects. Python allows all 3 kinds of programming. Since programming often works with collections of data, we'll often be applying a function to a whole collection. This fits nicely with the mathematical idea of a set builder or set comprehension. There are 3 common patterns for applying one function to a set of data. First is mapping. This applies the function to all elements of a collection. We apply some function, m, to each item, x, of a larger collection, C. Next is filtering. This uses a function to select elements from a collection. We use a function, f, to determine whether to pass or reject an item, x, from a larger collection, C. And the last one is reducing. This summarizes a collection. The details vary, but one of the most common reductions is creating a sum of all items, x, in a collection, C. We'll often combine these patterns to create more complex applications. What's important here is that small functions, such as m of x and f of x, are combined via higher-order functions such as mapping and filtering. This combined operation can be sophisticated even though the individual pieces are quite simple. The idea of reactive programming is to have processing rules that are evaluated when the inputs become available or change. This fits with the idea of lazy programming. When we define lazy properties of a class definition, we've created reactive programs. Reactive programming fits with functional programming because there may be multiple transformations required to react to a change in the input values. Often, this is most clearly expressed as functions that are combined or stacked into a composite function that responds to change. We'll look at some weblog data that has date-time string values. We need to parse these to create proper date-time objects. To keep things focused in this video, we'll use a simplified log produced by Flask. The entries start out as lines of text that are similar to these lines. We can, however, write a generator function which can process each row of the log, producing a more useful intermediate data structure. A generator function is a function that uses a yield statement. When a function has a yield, it builds the results incrementally, yielding each individual value in a way that can be consumed by a client. The consumer might be a for statement, or it might be another function that needs a sequence of values. This requires the datetime module, which we have already imported. Next, we define a function that processes a source collection. Here we've included the suffix _iter as a reminder that this function will be an iterable object, not a simple collection. After this, we include a for statement that visits each item in the source collection. The body of the for statement can map the item to a new item. In this case, we mapped a single field from string to a datetime object. The variable date is built from the string in item of 0th position. Then we mapped the log message 3-tuple to a new tuple, replacing the date string with the proper datetime object. Since the value of the item is a tuple, we created a singleton tuple with date and then concatenated this with the item oneTuple. Then we yield the new item with a yield statement. The whole construct looks as this one, properly indented. The parseDate iter function expects an iterable input object. A collection is an example of an iterable object. More importantly, though, other generators are also iterable. We can leverage this to build stacks of generators which process data from other generators. This function doesn't create a collection, it yields each item, so that the items can be processed individually. The source collection is consumed in small pieces, allowing huge amounts of data to be processed. In some videos, the data will start out from an in-memory collection. In later videos, we'll work with data from external files. Processing external files benefits the most from this technique. Now, let's jump right in to use this function. So, we move to the command line terminal and type a few lines of code. First, we import pprint and parseData iterator. Then we implement the for statement. Now let's print the item. And here's the output. Cool! Here, we've used a for statement to iterate through the results of the parseData iter function, one item at a time. We've used the pprint function to display each item. We could also collect the items into a proper list using this line of code. In this example, the list function consumes all of the items produced by the parseDate iter function. It is essential to use a function such as list or a for statement to consume all of the items from the generator. A generator is a relatively passive construct. Until data is demanded, it doesn't do any work. What if we don't actively consume the data? Let's see it now. The value of the parseDate iter function is a generator. It's not a collection of items, but a function that will produce items on demand. Writing generator functions can change the way we perceive an algorithm. There are two common patterns, mappings and reductions. A mapping transforms each item to a new item, perhaps computing some derived value. A reduction accumulates a summary, such as a sum, mean, variance, or hash from the source collection. These can be decomposed into the item-by-item transformation, or filter, separate from the overall loop that handles the collection. Python has a sophisticated construct called an iterator, which lies at the heart of generators and collections. An iterator will provide each value from a collection while doing all of the internal bookkeeping required to maintain the state of the process. A generator function behaves like an iterator. It provides a sequence of values and maintains its own internal state. Consider this common piece of Python code just for our understanding. Behind the scenes, something like this is going on. Python evaluates the iter function on a collection to create an iterator object for that collection. The iterator is bound to the collection and maintains some internal state information. The code uses next on the iterator to get each value. When there are no more values, the iterator raises the stop iteration exception. Each of Python's collections can produce an iterator. The iterator produced by a sequence or set will visit each item in the collection. The iterator produced by a mapping will visit each key for the mapping. We can use the values method of a mapping to iterate over the values instead of the keys. We can use the items method of a mapping to visit a sequence of key-value to tuples. The iterator for a file will visit each line in the file. The iterator concept can also be applied to functions. A function with a yield statement is called a generator function. It fits the template for an iterator. To do this, the generator returns itself in response to the iter function. In response to the next function, it yields the next value. When we apply list to a collection or a generator function, the same essential mechanism is used by the for statement to get the individual values. The iter and next functions are used by list to get the items. The items are then turned into a sequence. Evaluating next on a generator function is interesting. The generator function is evaluated until it reaches a yield statement. This value is the result of next. Each time next is evaluated, the function resumes processing after the yield statement and continues to the next yield statement. Now let's write a small function which yields two objects. So, we define the function and print the pre-yield and post-yield. Let's see what happens when we evaluate next function. Let's do it again. The first time we evaluated next, the first print function was evaluated, then the yield statement produced a value. The function's processing was suspended and the prompt was given. The second time we evaluated the next function, the statements between the two yield statements were evaluated. The function was again suspended and a prompt will be displayed. What happens next? We're out of yield statements. Let's try it. The stop iteration exception is raised at the end of a generator function. Amazing! You can visit this website for a challenging problem related to prime numbers less than 2 million. Parts of the problem seem obvious. It can be difficult, however, to test all those numbers for being prime. In this video, we saw how to write generator functions with the yield statement.